Swayam Prabha. Digital India. Educated India.
Welcome. We are discussing about shared memory and distributed memory in our course High Performance Computing for Scientists and Engineers, and this is the first module which is going on. We have already discussed about shared memory, cache coherence, and the advantages and disadvantages of shared memory systems, and this is the continuation of the lecture. We will now look into message passing in distributed memory systems, the advantages and disadvantages of using distributed memory systems, and memory management using both shared and distributed memory with an example focusing with examples rather we will say 3 examples focusing on matrix computing. Well, distributed memory means different computers, each with their own CPU and own RAM, own cache, connected via network switch to each other. Each processor has its own local memory, and this local memory is not visible to other processors. Neither it is mapped to a global memory space during computation. It is a local memory, it is local to everybody. Everybody has a part of memory, you have to work on, each computer knows that you have to work on this part of memory. You do not know what is with others. This is a distributed memory system. Each has different memory and different computers are doing different memory. Then what are they doing parallel? In parallel, they are trying to solve a same problem. Therefore, some of the information is needed from other processors. Say you need to establish continuity in between the processors, in some of the variable. So, in order to have continuity, some of the neighboring elements of the memory which might come from the next processor's memory. So, some information, or 4 computers are trying to do some calculation on one particular data, they are making maps in same or different data, same type of computation. Once this is done, they will exchange this and collect it, find out what is maximum, etc. So, they need to have some communication in between them, because there is otherwise nothing common in between them, but as they are solving one same problem, they need to communicate it. And due to local memory in each processors work independently. Changes made by in any variable by one processor do not readily go to others, but if they are working on the same problem, some of these changes need to go from one to other, and this is established by message passing. All the processors are connected to an interprocessor network. When a processor needs to be aware of changes in memory space which has been done by another processor, some memory element which is changed by the other processor, but as it's a same problem which all processors are working, one processor needs to know what the other processor has done. Like the first example, that a cot broken into or dismantled into 4 pieces will move from one building to other, and these 4 pieces are taken care by 4 different porters. Now, when they will go to the next building, they need to put everything together. So, first they need to see whether they are going to the same place and whether the pieces are coming one after other, what should be their arrangement. One porter not only can take care of his own part of the cot arm, but he also needs to see what others are doing. Some information, not the exact detail, all the details, but some information from what others are doing. So, some information has to come from one processor to other processor. A processor needs to be aware at certain stages, the processor needs to be aware of the changes in memory space which is done by another processor. Then explicitly this information has to be transferred from one processor to the other processor. So, the programmer has to identify the locations where one processor needs to get some information from the other processor, and programmer has to specify some construct which we will see later if this can be done using message passing interface or MPI. programmer needs to write some constructs which will say, hey, you have the processor 0, you have to transfer this information, this packet of data to processor 3. So, it has to be explicitly done by the programmer that this information from this processor will reach to this processor. So, in a sense there will be an interprocessor communicator or IPC framework which will allow each of the processor to exchange data with the other. So, all the processors are, and there should be, so this does not show a complete IPC connection, all the processors, therefore, these two processors, they will also share an IPC communication. So, all the processors should be able to communicate among each of them. That means, data from one of the processor can go to any of the processors in the network, that flexibility has to be given, and the programmer will specify which processor at which instance send what type of data to which processor, and explicitly one processor will send the data, explicitly there will be another processor who will receive the data. Say I have to pass an envelope to my friend, if I give him the envelope, he does not take it, then the message passing is incomplete. So, one gives, another has to receive, and all these things have to be explicitly defined in the program. The interprocessor communicator IPC is done through network. Programmer is solely responsible for putting data transfer constructs in desired places of the program. In shared memory, you write, you have to update this variable, some changes has been made by the variable. It is the back end, it is the compiler, it is the library functions, it is the message passing infrastructure or message parallel infrastructure, which is parallelization infrastructure, which is taking care of taking one packet of data and sending it through network cable or bus from one processor's cache and sending it back to the main memory, and then the copies are going to others cache. That is in shared memory, but in distributed memory the programmer has to write that this information will go to, from this processor will go to this processor at this instance, and this processor will receive this information. The compiler or the library functions or the interfaces or the parallel architecture, hardware architecture, now no one is going to take care of that. It is the programmer's responsibility to ask all the back end things like compilers and interface, etc., APIs, etc., to ensure that this data transfer is happening. We can give an example. We are solving a Laplace equation in a large domain, and it is broken into 4 subdomains. We will come back to this problem when we will look into MPI programs, and each of this program is solving the same equation on a smaller domain, on the subdomain. This is called a domain decomposition technique. However, in order to ensure that this variable t, whose Laplacian is called here, Laplacian means second partial derivatives del 2t del x square plus del 2t del y square here. So, in order to solve this, we need a continuity between t, and while again solving the Laplacian t is equal to 0, here we need a boundary condition. Both boundary conditions or the continuity will be ensured by passing the value of t from this location to this processor and getting the value of t here to this processor's memory space. Therefore, data transfer will happen across the processors while solving this equation. So, the procedure for solve this equation is that you take the last updated data in this processor, solve the equation is this domain, update this variable, send it to this processor who can solve his equation using this update. Again, the updated value at this processor will come to this processor while solving this equation. So, a dynamic exchange of data during each stages of calculation is required in different processors, and this is ensured by a framework like this, where all the processors can send data to each other. Now, one thing can be seen that if one is sending data from here to here, the processors are physically close and these processors are physically distant, it is possible. So, the data transfer time will be more. So, therefore, some data localization, some processor localization, these things are important, and we will again discuss these issues when we will look into how to improve the performance of parallel computing. in distributed memory systems. A simple Ethernet switch can handle this interprocessor communication. However, fast networks like gigabit, 10 gigabit Ethernet, 100 gigabit Ethernet, MIDI-NET, InfiniBand switches, they are used because it is a good amount of data which will be sent, and if the data transfer time is much more in much orders more than the computing time, the performance will be bad. So the good supercomputers, good HPC platforms use fast networks for data transfer. The advantages of distributed memory is that memory is scalable with number of processors. As we increase number of processors, the memory is geometrically increased. This is not a common memory space where all the processors are connected. Each processor has its own local memory space. So, if we have a very large problem, we do not need to be constrained by having a same contiguous memory space. It is different small local memory units. As I am putting a new computer, it is coming with its own local memory, and therefore, the total memory of the problem is increasing. Each processor rapidly accesses memory without traffic or contention, because each one is using its own memory, own cache, it is a local memory only. Therefore, the cache update it's not important that from some other processor's memory or from some other remote memory's location, cache update is coming to all the computers, and there is no question of having inconsistent cache. Each cache is decoupled. So, this overhead can be removed, the contention or traffic due to access of the same memory and cache consistency overheads. High-end motherboards and large RAMs are not required. Simple community machines, some good servers, they can be connected by a switch, and we can make a large distributed memory platform. It is a cheap system. Another very important thing is that as the memory is scalable, we can break down a large problem into many small memory problems. We really don't need to think about handling, programming wise also handling a very large memory problem. So, the net memory can be also broken down, and each computer is accessing a small part of memory, which is good. Disadvantage is that programmer has lot more duties now. He is responsible for each data transfer. He has to know all the details of the data transfer, and he has to specify when, which data, which type of data, what should be the data size will go from one processor to other. He has to ensure that the receiving processor is free to receive the data, all these things. So, programmer has to handle much more complexities compared to shared memory. And in case there is a global data structure, breaking it down to small local memories, and then once the solutions are done, mapping the all local memories into a global data structure, it is also sometimes a complex problem. So, there are much more complexity compared to the shared memory space problems. You need to important steps are that there is a very heavy requirement of synchronization, because there is more flexibility, more synchronization is required. All the computers are working on different data, the data size may be different, the operations may be different also, but if you are solving a same problem at several stages, you need to see that all the arms of the cot is together, so that you can get back the final cot. So, you can assemble it. So, synchronization is required. On fly data consistency may have to be ensured, like that solving a Laplace equation, that while doing the iterations for the matrix solver for the Laplace equation, you have to see that the T field or temperature field is consistent. So, you need to do data transfer or check some of the data consistency on fly at different programming instances. And finally, the results have to be assembled using some of the mapping to a local memory. Important pointers are there. A large problem, what we have discussed in last slide, a large problem can be broken down into many sub problems with less number of operations and reduced memory requirement. As the problem is broken down into small problems, each problem requires a small memory. Therefore, a computer with a small memory can handle the sub problem. Therefore, you do not need to use a large memory. Also, you do not need to operate over a large actually a large address space, which is good. Memory accesses are local to a particular node, and overheads are less, conflicts, contentions are avoided, and one computer is accessing one memory, therefore high bandwidth is obtained. However, communication among the processors are required. At different programming instances are to be written to ensure this communication. Latency and bandwidth in the interconnectors, this has to be looked upon. Communication through a PCI bus is much faster than communicating through a very fast mini-net switch. Therefore, there will be more latency because communication itself has its own latency, as well as there will be less bandwidth because now it is going through a network switch. So, communication has to be some way reduced or localized so that this latency and bandwidth issue that can be handled. Larger, and it has larger communication time compared to shared memory. Contention time, conflict time, overhead, these are gone, but communication time for any single communication time is much larger compared to a similar shared memory platform. So, we summarize some of the important architectures. One is a uniform memory access shared memory system, centralized computers with uniform memory access, and these can be symmetric multiprocessors, some of the IBM machines, SGI challenge machine, etc. The APIs which can be called to parallelize these are MPI, threads, OpenMP. We will discuss about MPI and OpenMP later. This machine can be scaled to tens of processors, 20, 30, 40, 80, 100 processors can be put in a single motherboard or single bus or an interconnector which is connected to the same piece of memory. And the drawback is that memory CPU bandwidth, because many computers are trying to access the same many processors are trying to access the same memory, also cache coherence, etc. there. A large number of softwares, independent software vendors, almost everybody's program software is written for this type of array arrangement, the uniform memory access, centralized computer arrangement, shared memory system arrangement. The next one is non-uniform memory access, IBM Power 4, HP Exemplar, SGI Origin, they are examples of that. Again, similar software APIs like MPI, OpenMP goes there. This can be scaled to hundreds of processors. So, many processors, 100, 200, 300, 500 processors can be put into an interconnect switch, and they can, though they are computers with different RAMs, but this memory can be mapped into the symbol into the shared memory space. And again, the issue is non-uniform access times and memory CPU bandwidth here. However, almost all the software vendors provide software for this type of system. So if we see, these two are the basic shared memory system. The best thing of shared memory system is that there are thousands of softwares for shared memory system. So, you do not need to write anything most likely. You will get a program which will run in your shared memory system. The distributed memory system, instead of all different communicator APIs, only one communicator is universally accepted to work on the distributed memory system, which is MPI. Good thing is that it can be scaled over a large number of processors, thousands of processors can be connected with each other. The drawback is system administration is hard, program is hard, it is hard to develop a system and maintain this because many computers are connected via switch. What is the health of each of the computers, how to monitor whether one is free, whether one is working fine. You need a good scheduler so that different jobs can, different SPMD jobs can work together. If there are thousands of processors, maybe you are not, your own program is not using 1000 processors, somebody else is also using some of the processors for his own program. So, a scheduler is needed so that these jobs run well without hampering performance and bandwidth, etc. And very less number of independent software vendors actually write program for supply program for distributed memory architecture. So, many times you have to be a programmer yourself to work on a distributed memory system, because the standard available programs, commercially available softwares many times do not work for distributed memories. So, another is hybrid architecture. The leading supercomputers use hybrid architecture where distributed memory platform is given, but each of the distributed memory system is also uniform memory access SMP, symmetric multiprocessor, that they are connected with each of the box has multiple processors connected with the same memory, and it can give you it can actually scale up to millions of processors. So, it is called a hybrid memory architecture, which is a distributed memory in some sense, because all these are acts as distributed memory computer, and this one or any of this acts as a shared memory parallel computer. So, it is a distributed cum shared memory hybrid memory architecture. Now, we look into some of the simple matrix operation programs and see how are the memory management done for that. So, one is a dot product. We have to consider vector multiplication. Vector A multiplied with vector B gives the scalar C, which is C is equal to A1 plus B1 plus A2, A1 B1 plus A2 B2 up to AN Bn. Now, we will assume that these are large vectors, million size vectors, and hypothetically or as a thought exercise we will deploy parallel computing architecture to get the vector product, matrix vector product, etc. So, if we have NP processors, let us assume that n is the number of elements in one vector, number of rows, the total number of element is n, therefore, each processor is getting NP by n, which is m number of elements in A and B. So, what each processor will do, will take this m number of elements, get the sum, and all the processor will get the sum, and finally they will get a final sum. If we use a shared memory, we have say NP processor ID starts from 0 goes up to NP minus 1, and first processor is doing C is equal to C plus A1 B1 A2 B2 AM BM. Why it is writing C? Because all the processors cannot concurrently write the same variable without using some protocol. So, they are using the protocol sum, everybody is writing to the sum, writing a sum. So, they can add up to the variables. Processor 2 writes C is equal to C plus AM plus 1 BM plus 1 2A 2M B 2M. Processor 2 writes so, processor NP minus 1 writes so. So, as the processors operate in parallel, finally when the operation is done, we get that the C has been updated by all the processors. So, it is the same variable C which all the processors are updating simultaneously using some concurrent write option of the sum protocol, and each of the processor is some way applying this Fortran programming snippet for m elements. Write C is equal to C plus the particular location which is given allotted to this processor to work on of A matrix into B matrix and do and do. So, this is the same programming instance which will be running by all the processors. We are not writing different programming instance for different processors. This will run by all the processors, and how all the processors will work together, that will be ensured by some API like MPI or OpenMP. Simultaneous access to C is by all the processors through the do loop. So, in this do loop all the processors are simultaneously accessing C. So, there is an issue of cache coherency, though this is a concurrent write protocol which some way is allowed to handle the cache issue. However, the cache updates are required by all the processors, and during each of the instance of this do loop, each of the run of the do loop, this cache coherency is established across all the processors, which is probably adding to overhead due to cache coherencies there. Well, but the programming is simple, it's the same line which will be executed by all the processors, and it's the same matrix we have to see. Now, if we look into the distributed memory, it is same that each processor is working on m number of elements. So, each has its local memory. The first processor has A1, A2 up to AM, B1, B2 up to BM on which it will work. It stores this as a part of local memory, A1 hat, A2 hat up to AM hat, B1 hat, B2 hat, BM hat, and it operates C hat is A1 hat, B1 hat plus A2 hat, B2 hat up to AM hat, BM hat. What does the second processor or processor 1 does? it is also working on the local memory, which is A1 hat, B1 hat, A hat, B hat, but it stores a different element of the main vector as the local memory. So, some of the distribution algorithm load allocation algorithm has to be run by each of the processor, which can do this. A1 hat is not A1 but AM plus 1, A2 hat is AM plus 2 and so on, and it executes the same line and gets its own C hat. Processor 2 similarly gets different data as A1 hat and A hat and B hat and finds its own C hat. Each processor gets their own C hat, same up to processor NP-1. And once this is done, now all the processor knows that everybody has finished calculating their own C hat, writes the final C is sum of the C hat by all the processors. So, this C hat which is coming from all the processor has to be communicated to one processor or to maybe to other processor. This has to be communicated to all. So, communicate a single, and this requires C hat is a single value. So, communicate a single value from after the entire calculation, communicate a single, synchronize it, say that everybody has finished their calculations, and communicate this single value to each processor or to a master, make a one node master which we will collect all the C hats and sum them up, and use a reduction algorithm like gather all the values and find their sum, which is I mean very simple distributed memory communication in distributed memory communication protocol, and find it. So, they are operating separately. The first one operates directly into the address space. There is an issue of cache coherence. Second one does not need to do any cache coherence distributed memory system, but needs to map the global memory into local memory and then do synchronization that everybody has finished calculations and communicate the output from all of the local memories to one computer's local memory and sum them up. Well, we go to one order more complexity, it is a matrix vector multiplication. So, A11, A12, A1P, M into P matrix, M rows and P columns multiplied with a P row vector, and we get a M row vector as the product. If in shared memory, the first processor operates on the first row of the A matrix, gets the first row of the product vector. Second processor works on the first row of the A matrix, second row of the A matrix, and gets the second row of the right hand side vector, and so on. So, all the processors will be knowing the B vector, all the processors knows the entire matrix, all the processors are working on the using the same B vector, operating only on the rows allocated to the processors and writing the rows here. In shared memory application, different processors operate on different rows of the matrix and get different elements of the product vector. No contention in writing because they are writing at different locations of the memory, and the cache coherence is also not required if we know that we are not going to access the cache which is access any of the others memory. We don't need to make it cache coherent, it is disjoint cache program. However, false sharing may rise because when writing this, it might take the next line in its cache. So, the second processor may not be able to work on this because this is the first processor is writing here. So, there can be, though there is not actually sharing of the output variables among the processors, but as they are in the same address space, there can be some way the cache lines are being shared, not exactly the cache element, but the next elements in the same cache address may be shared, which is called a false sharing, and that can add to overhead. If we come to distributed memory system, each processor has been given few rows of that, and each processor is getting a part of the vector independently, and finally these elements of the vectors has to be communicated to one of the processors and it has to assemble the entire result. So, each processor is operating on its own address space, it is looking at first two rows only. Each processor knows that it has been given 2 rows, it has to operate on these 2 rows. What is the location of these 2 rows? It does not know. Some processor knows, or there is some mapping for that, but while operating it does not know. It has 2 rows, it is operating only on these 2 rows and writing 2 rows of the vector. Finally, this data has to be communicated to one processor and then they will be assembled, all these will come to their respective positions. So, this will come here, this will come here, this will come here, respective position, this will come here. All of them will be assembled together to form the final matrix. So, you need communication of these elements, you need communication of these elements and agglomeration and mapping to the final matrix. Elements of vector C, which are few numbers, they are to be transferred from each processor. The final assembly is required. Vector B, interestingly, this vector B is known by all the processors. So, this is, though this is a common vector, but this is stored in local copies. This is stored as local to all the processors. Rows of matrix A, instead of being an M into P matrix, O into P, small o into p rectangular matrices are stored in all the processors. So, all the processors are storing a part of memory, not the entire memory. Now, the more complicated issue can be a matrix multiplication. So, there is a matrix M rows, there are P columns and another matrix with P rows and N columns multiplied to get a M row N column matrix. So, any ith row of this matrix is all the elements are sequentially coherently multiplied with the columns of the matrix B, jth column, and you get the ijth element of the product matrix C. So, in distributed memory, either a row matrix has to be partitioned or the column matrix has to be stored, and the column matrix has to be stored or vice versa. So, part of the matrix is the row matrix, in the row form, the left matrix is partitioned, a part of that given to one processor. It operates on the entire column matrix and we get a part of the right hand side matrix. So, this matrix has to be stored, this matrix which is the right hand side matrix, that has to be stored in all the computers. Processor 0 will do that. Each processor, the next processor will get a part of the matrix and do that. So, each processor will produce a matrix, and this finally you need to communicate a matrix, you need to now communicate a large amount of data which is not a scalar, not few elements of the vector, but it is a small matrix. So, the communication overhead will be more, and each processor has to also store the entire column matrix. So, parallelization, that means that even if you are parallelizing it, but really you cannot do anything with respect to the column matrix here, at least in a simple form of matrix multiplication distributed memory algorithm, because you have to operate over all the columns here, and that is in a sequential manner. This is known to all the columns. But if this column is block structured, say there is some element like this, some elements are non-zero in the column, some elements are non-zero and most are 0 in the column, some elements are non-zero and most are 0 in column. You can much easily parallelize it, that some of the blocks are allocated to some processor, it knows that this row will be multiplied with this block only. And if it is not block structured, but it has many non-zeros and many zero numbers, which is called a general sparse matrix, a graph partitioning can give a better parallel algorithm. And if we think of a shared memory, all the products add to the common memory space, and there can be contention and cache coherence, because there will be same cache lines which will be shared across many processors and they are writing to the same memory space. However, accessing a row, if the matrix is the cache reads the matrix in the row wise, when one matrix will be accessed along the column wise during multiplication. So, we take one column, one row, multiply them, take a dot product and get one element. So, one column will be accessed, it is not a contiguous memory. So, there will be something related with the cache hit ratio, it will thrash the cache size, because some elements of the memory has to be read and different cache lines has to be created, and across many processors it will give us a undesired performance. A better algorithm in shared memory. So, now we can see both distributed memory has some issue in terms of parallelization, though we are parallelizing it, we cannot do anything with the right hand side matrix in a simple version, we need some algorithm to parallelize for the right hand side matrix also. Similarly, shared memory, it leads to some issues with cache. So, one of the ideas can be that you allot some rows and some columns to each of the processor's workspace, and when multiplying it will write back a group of elements, a tile of elements which has number of rows and number of columns here, so that this cache is filled with this element, this cache is filled with this elements, they are writing it here, and in some sense, so what will happen, like these two are multiplied and all the rows and columns are multiplied and this group of numbers will be obtained. And instead of next operating in the next row and next column, subsequent row and column, which will give a false sharing, operate in a another row, give some gap, operate in take another row and take another column, get a product here. So maybe you can take some of the rows here, some of the rows here, some of the columns here, and the product will be here. So there is no cache line sharing and there is no false sharing, cache coherent, disjoint caches are used and you can get better performance there. Programmer can make red black arrangements, that few reds will be multiplied at one instance, then the blacks will be multiplied, and avoid false sharing, contention and traffic, and can get a better solution. So for more complex problems, the programmer needs to think of algorithms which are taking care of some of the issues we discussed in computer architecture, parallel computer architecture and parallel computer memories, which once kept in mind and the program is written looking into these aspects, you can get much better performance using parallel computer. So using a supercomputer doesn't ensure that you are getting best performance. You need to know, you need to think from the architecture point of view and need to know the right things, by doing which you can get better performance and the best performance, say. Well, so we finished shared and distributed memory discussions, and these are the textbooks along with Wikipedia notes I have followed. We have looked into shared memory and distributed memory in detail, hotspots like cache coherency and message passing, which reduces the performance, are discussed, and memory management for matrix computing using both shared and distributed memory are introduced to today's class. Thank you.